Okay, so let's go through this.
Good.
So let's look at the outcome-based estimate.
Good.
I think you kind of gave me everything I need here.
Yeah,
So
it's possible I spelled it out too detailed.
you could never spell it out in too detailed a way, Michael. So if I look at it, we encounter S2 exactly once.
Exactly once.
And so the average of 1 is pretty easy. It's that thing.
Okay, and what is the estimate for that one?
Well, 2 plus 0 plus 10,
Yeah,
which is 12, because gamma's 1.
because gamma's 1. So, good. So this is saying because we've only ever encountered S2 once, and the one time that we saw it, we ended up with a reward of 12 getting to the final state. That's going to be our estimate. And that's what TD1 would actually do, modulo the learning rate and how you initialize the values and so forth. But that's sort of what it's trying to be like given this data.
Right.
All right, so now does that match with the maximum likelihood estimate, the estimate that we'd get if you used the data to build a model and then solved it?
So for the maximum likelihood estimate, all I really need to do is to compute, let's see, the probability from going from S3 to S4 and the probability of going from S3 to S5, because everything else is deterministic. And in all 5 of those transitions, I get to see every state and every reward. So I have everything that I need. So let's just go ahead and estimate the probability. So looking it through, I go from S3 to S4 3 times
2, 3
out of
5 times that
5.
we're in S3.
Right.
Good. Uh huh.
So that would be 0.6.
3/5 is 0.6. Yes, got it.
All right. And by process of subtracting, that means that going from S3 to S5 happens 0.4 of the time.
Yeah.
All right.
And we could compute that directly too by just counting. We get twice out of 5 times.
Right. So those aren't right. It should be 0.1, not 0.4, and it should be 0.9, not 0.6. But hey, it's the data that we've got.
Yeah, and yeah, you're right. I mean, it's much more even, but it is still S4 is more common than S5.
Right. Okay, good. So with that, I can just, propagate values backwards through the MDP, just like we did on the final exam for 7641. Okay, so
Good.
so let's see. The value of SF is 0. The value of S4 is 1,
Mm-hmm. One more.
1 plus 0. And the value of S5 is 10
Good.
plus 0.
All right. So, and that's all actually correct.
Yeah, that is actually correct. Thank you, determinism. Okay, so S3 then, 6/10 of the time we'll get a value of 1, and 4/10 of the time we'll get a value of 10. So that would be 0.6 plus 4.
4.6.
That is indeed 4.6.
Cool.
All right, so who cares what S1 is, but I guess we can go ahead and compute it. It would be 5.6
Good.
because it's plus 1, 4.6.
But the actual question was about S2. Dun dun dun.
And so it is 6.6.
6.6.
Proof by addition,
All right.
and it works out pretty well. Okay, so 6.6 is very different from 12.
Sure.
I'm not sure if either one of them is right. So let's see. If I recall, when we went over this MDP before, using the actual transition probabilities, 0.9
Yep.
and 0.1, we figured out that the value of S3 was 1.9.
Yep.
Yeah, and we can check that. Like that would be 0.9 times 1 plus 0.1 times 10. So yeah, that'd be 1.9, which means the value of S2 would be 3.9.
All right. So the actual value is 3.9. The maximum likelihood estimate is 6.6, which is more, but the outcome-based estimate is 12, which is a lot more.
Right. So everybody's wrong except for 3.9, but maximum likelihood estimate is less wrong.
Right. And so why in this case? Like what's the difference between these cases? First of all, why are these so far off? And second of all, why is the outcome-based one even further off than the maximum likelihood?
Well, I think it's pretty simple, right? When we computed the outcome-based one, we basically only used one of the 5 trajectories to propagate information back. But when we did the maximum likelihood estimate, we used information from all 5 of the trajectories, even though we only encountered S2 once.
Mm-hmm.
And so that's just more information and it's more accurate. And you would imagine that if I triple the amount of data, the 6.6 would very quickly get closer to 3.9, and the 12 might not move at all if I never see S2 again.
Good. So this maximum likelihood estimate is actually using more of the data. I think that's accurate. The reason it's higher than it should be is because we got, I don't know, lucky, I guess, and had a bunch more transitions to the high reward state S5 than we would expect on average. And we got really unlucky, or really lucky, depending on how you think about it. From this one trajectory we did from S2, we got the unlikely outcome, which is high reward, and so we ended up with an estimate that is way higher than it really should be.
Yeah, but look, if let's imagine that we had gotten lucky the other way. There's only one other possibility, right? S2 to S3 to S4 to SF. And if that had happened, then we would have seen a value of 1 instead of a value of 10, and we would have had 3.
That's right. And on average, it's going to turn out to be the right answer, this 3.9. But this estimate is based on the limited data that we've got.
Right. Okay, fair enough.
All right. So, but the punchline here is that this TD1 idea, it's not using all the data. It's using just individual runs. And so when a rare thing happens on a run, you could end up with an estimate that's quite far off. And it could maybe stay that way for a long time. Whereas the maximum likelihood estimates seem to push you in the direction of using the data that you've got to do the best you can. And so what this is pointing out is that maybe we don't want to just do TD1. There's some nice things about TD1, but maybe we can shore up some of these other issues and come up with something even better.
What, without actually building an entire model?
Yes.
Okay, well, I look forward to that.